Hello everybody, I am Dr. Aziz Arbai and I present my work, the probability law distribution of LBDGP birth and death processes. We mean LBDGP, general linear birth and death processes. In this article, we consider the case of birth-death processes, BDP, with an infinite number of states and birth-death rates that are constant with respect to the number of states. We determine the deterministic solution, the distribution of BDP, of the Kolmogorov differential equation for the general linear birth-death processes, GLBDP, similar to Kendall processes by considering the birth and death rates as following. In this paper, we present our unique and efficient method for calculating the n power of 2-2 matrix without resorting to the traditional diagonalization method. Our main contribution is demonstration of the practical utility of this new formula in two important areas. So, first, solving second order linear recurrent sequence, treating the birth-death processes with an infinite number of states, presentation and solution of general linear birth-death processes. First of all, we give the power of any 2-2 matrix without diagonalization. Diagonalizable or not diagonalizable, as following in this theorem. So A power n, just to have alpha 1 and alpha 2, who are solution of this determinant. Here we give a remark with two cases: if the eigenvalue is equal or not. After we present our application, firstly we applied with the linear recurrent sequence order 2 problem. Second order linear recurrent sequence is a sequence in which each term is defined as a linear combination of the two preceding terms. So you verify this relation. So after we applying our formula to matrix n power, we have the results of the un. Just it's simple, general, and we present a remark. We have two cases, distinct, and after we present our second example of application with the birth-death processes, BDP. The birth-death processes is classically example of a continuous time discrete state Markov processes that is used to model population growth over time. It was introduced by Fuller and has been used in various fields such as biology, physics, ecology, quantum theory, computer science. Mathematically, birth and death processes are often modeled using systems of differential equation called direct Kolmogorov equation. This equation describes the evolution of the probability distribution of the number of individuals and systems over time. However, this equation can be notoriously difficult to solve analytically or even impossible, especially for complex systems with no constant birth and death rate. This paper built upon our previous work, which laid the foundation for this approach. However, the current study extends and refines these methods, making significant new contributions, especially by applying our formula that gives the n power of any 2-2 matrix. So let xt be the discrete and homogeneous birth and death stochastic processes. Verifying the relation, this system relation with lambda e is the birth rate and mu e is the death rate. So proposition, we have this backward equation with the matrix A is a matrix 3 diagonal. So let's be beta an eigenvalue of the matrix A and X and an associate right eigenvector of A. So Ax equal beta x. So we have this system of equation. So we considered first the case of lambda and mu constant. So we have this system of equation who the solution be xn equal xn this sum. So let's delta equal dependent of lambda, mu and beta. There are two cases. If delta equals 0, so xn as follow, and if delta different 0, xn has this formula. And for we look and apply our results in the linear birth-death general processes or LBDGP. In this subsection we saw the linear birth-death processes as the candle processes. The backward equation is as follow. So the system of equation for K is as follow. The left eigenvector in the same way and the method that we use it to determine the right eigenvector Ax equal beta x. We do it to find the left eigenvector y such y a equal beta y. So we have this system and we resolve it. So we consider also the two cases. If delta equals 0 or different 0, we have yn. So the probability law of the linear birthday general processes, doing the variable change, f x t equal u x p t, where u is the left eigenvector yk. So the equation change to just like this. We simple to resolve, and we have f who is y1 exponential xt is equal as this sum. So first case, if lambda, if delta is equal to 0, we have this discussion, and we describe exponential like this series. So, and finally we have p, the distribution, the formula of distribution in this case is simple. This is a remark for p0t. Second case, if delta is different 0, we have our yn and exponential, and we do the same as the first case, but this time we have a difficult equation to resolve, and we do another variable change g, and who is g, and this g function have a major difficulty as an associated singularity at x equal to 0. So consequently it doesn't admit a power series, Taylor series around x. However, it does admit a Lorentz series around x equal 0. And we do Lorentz series of gx around x equal to 0. And finally, we have formula of PNT as that is following. Conclusion: this article builds on our previous work 1, 2, and 3, which laid the foundation for this approach. However, the current study extend and refine this method, making our new innovative contribution more precisely. We outline the method for searching for the probability of distribution of bird and death processes in the general case. It remains to be seen whether we can apply the same trick as in 9, like in 5, 9, and 11, with well-chosen conditions to construct our assess the existence of the positive measure. Thank you, and see you later.